Dynamic equilibrium. There are two types of reaction, non-reversible reaction and reversible reaction. Non-reversible reaction is a chemical reaction proceed in only one direction. For example, carbon reacts with oxygen to produce the product carbon dioxide. The reaction proceeds from the reactant to product only one direction. Reversible reaction is a reaction which takes place in both forward and reverse directions. For example, calcium carbonate form calcium oxide and carbon dioxide as the products. Calcium oxide can react with carbon dioxide to form calcium carbonate. The top arrow, half-headed arrow, means a forward reaction. The reaction proceeds from left to right, from reactant to the product. The bottom arrow, half-headed arrow, backward or reverse reaction, means the reaction proceeds from right to left, from products to become the reactant again. Reversible reaction, for example, the reactant A produces the product B reverse back to become the reactant A. In a reversible reaction, initially the reaction proceeds toward the formation of the products, means first from reactant to become the product. As soon as some product molecules form, the reverse process begins to take place, means as soon as some product molecules forms, the product can become the reactant again. Reactant molecules are formed from products molecule. For example, here is a graph of concentration against time. This is concentration of reactant A, square bracket means concentration, decrease with time. Initially, we have the concentration of A. Let's say our A is N2O4. Initially, we have the concentration of the reactant, and initially we have zero concentration of the product. Let's say our product is NO2. So we have a certain amount of reactant, concentration of reactant, and we have no product initially. As the reaction takes place, the concentration of reactant decrease with time and the concentration of the product increase with time. This is the concentration of reactant decrease and the concentration of the product increase with time. After a particular time 1 here, for example, concentration of A and concentration of B remains unchanged. The concentration keeps constant, remains unchanged. It doesn't increase, it doesn't decrease, it remains unchanged. When both of the reactant and the product concentration remain unchanged, the system is in the state of equilibrium. Dynamic equilibrium is achieved when first, the concentration of reactant and product stop changing or remain constant over the time. Second, the rate of forward reaction is equal to the rate of reverse reaction. This is the rate of the reaction, both rate of reaction forward equal to the rate of reaction reverse. Third, the reaction quotient Q equals with the equilibrium constant, means the value of Q is equal to the value of K. So these three conditions have to be met to say that dynamic equilibrium is achieved. For example, N2O4 as the reactant produces 2NO2 as a product. The equilibrium is a dynamic equilibrium, means that after T1, here at a particular time T1, the reaction did not stop, but the forward and reverse reaction occurring at the same rate, means the rate of the forward reaction means the forward reaction, reactant becomes a product, and the rate of reverse reaction, the product becomes the reactant. Both reaction rates are the same. The concentration of A and concentration of B remain constant means no net change. The concentration are not the same. The rate are the same for the product and for the reactant. The rate are the same, but the concentration are not the same. The concentration remain constant or no net change for both reactant and the product. As N2O4 is the reactant. As reactant is consumed or reactant is used, means the reactant decrease because it's being used to produce the product, the rate of the forward reaction decreases. Forward reaction means from reactant to become the product. The rate of forward reaction decreases. As NO2 is a product. As NO2 is formed, as a product is formed, the rate of reverse reaction increases. Reverse reaction means the product becomes the reactant. So as the product is formed, the rate of reverse reaction increases. As the two rates become equal, an equilibrium state is attained and there are no further changes in concentration. Concentration remain constant, remain the same, the concentration no further changes, but note that the concentration of reactant and the concentration of the product are not the same, just there is no further changes in concentration for both. Both rate of forward and rate of reverse are equal. Then we can say that equilibrium state is attained. Law of mass action, also known as law of chemical equilibrium. The relationship between chemical equation and the expression of the equilibrium constant. The law of mass action states that for a reversible reaction at equilibrium and a constant temperature, a certain ratio of reactant and product concentrations has a constant value of K. K is equilibrium constant. So law of mass action relates K with the concentration of product and reactant. This is a ratio. On the top part are the concentration of the products. Top part is the concentration of the product. Our product C and D. Our reactants are A and B. So K equal to concentration of the product. If you have C, D, E, F, G, you have to put all the products on top, and over concentration of all the reactants. Our reactants are A and B. So concentration of A and B. The small letter A, B, small letter C, small letter D is the stoichiometric coefficient for reacting species. A, B, C, and D means how many more of A, how many more of B, how many more of C, and how many more of D. The small letter, the number of more stoichiometric coefficients. And if you put in this equation, it will become the power. So the stoichiometry of C is the power of the concentration of C. Stoichiometry of D is the power of the concentration of D. Same goes for A and B. Although the concentrations may vary, as long as a given reaction is at equilibrium and the temperature does not change, the value of K remains constant. It's just the same value of K remain constant as long as reaction is at equilibrium and you don't change the temperature. Even though you change the concentration, the value of K remain constant when these two remain unchanged. Equilibrium and temperature does not change. Curve of reversible reaction. For a particular system and temperature, the same equilibrium state is attained regardless of how the reaction is run. Means no matter if you start with product or you start with a reactant or you start with both. So the same equilibrium state can be attained. Let's start with NO2. When you start with NO2, you look at NO2 as the product. When you start with the product means you have no reactant at first. So reactant N2O4 N2O4 concentration 0 initially. At time 0, when you haven't started the reaction, at time 0, there is no reactant because you start with the product NO2. If you start with the product NO2, you need to have a particular concentration of the product. So that's why it starts at above concentration. It has a value of concentration. The product has a value concentration, and for the reactant, no concentration because you start with product. So concentration of reactant 0. When you start with the product, as the reaction takes place, the concentration of the product decreases and the concentration of the reactant increases because the product converts to become the reactant. That's why the product decreases, concentration of the reactant increases because it formed from the product. Next, when you start with N2O4, start with N2O4 means you need to have a concentration of N2O4 initially. As the reaction takes place, the reactant N2O4 decreases because N2O4 is converted to become NO2. So initially 0 concentration of NO2 because you start with reactant means no product at first. As the reaction takes place, the concentration of the product NO2 increases. Next, if you start with both NO2 and N2O4, you need to have both concentration initially. So both cannot be 0 if you start with both. So both reactant and the product has a particular concentration, an amount of concentration. N2O4 is the reactant, increase, and O2, the product, decrease. And when at a particular time, the forward reaction and the reverse reaction are the same, means the concentration of product and concentration of the reactant remain constant. No change in concentration of product and reactants after equilibrium state is attained. Even though equilibrium is reached in all cases, the equilibrium concentration NO2 and N2O4 are not the same. As I've mentioned earlier, the rate of forward and rate of reverse are equal. They are the same. The rate of the reaction forward, rate of reaction reverse are equal, but the concentration of product and reactant are not the same when the equilibrium is reached, means concentration product, concentration of reactant, concentration of both solutions are not the same